While this is our first year competing in the University Rover Challenge, we've been working hard over the past year to build our team and create our current rover, Icarus. We started as a team of 4 mechanical engineering students, and now we have 30 dedicated members working on cohesive, multidisciplinary teams.
And fostering the development of professional and technical skills. While we're working hard to meet technical specifications and solve the URC problems creatively, we cannot be more proud of what we've accomplished thus far.
Over the past year, the mechanical team has designed, manufactured, tested, and iterated a functioning Mars rover chassis. This was accomplished by using a rocker bogie suspension system with 2 parallel sub-assemblies on both sides of the rover.
The rocker bogies connect using a stainless steel shaft, simultaneously allowing each side of the rover to move independently and self-balance itself, which is pivotal for traveling on uneven terrain. This shaft supports the central housing unit, which contains all necessary components for each of the respective missions. The central housing unit is suspended beneath the shaft to lower the center mass of the chassis, which allows for more maneuverability and control when climbing up steep inclines. The beach wheels were chosen because of their ability to drive on sand and their durability and flexibility when rolling over sharp and stiff objects.
Our mechanical arm is currently undergoing prototyping as we refine our design. We will be using 2 main linear actuators to both pivot the shoulder and elbow of the arc. The base will rotate with a geared DC motor. Our end effector will feature a 360-degree rotation gripper that can also grasp, an adjustable hook for heavy lifting, and a finger for precision tasks. All control systems will have position sensing capabilities, with amplified potentiometer readings for the linear actuators and servos, and encoders for the DC motors. We will feature 2 means of controls, the first of which will use inputs of the PS4 controller to control each axis. The second means of control will use inverse kinematics to adjust each axis to a solution for the desired end effector positioning. This allows for simplified operation.
Our team has been working on developing a radio and communication system and setting up the rover's autonomous navigation system, which uses a combination of neural network learning, object detection, and automatic steering.
Our communication system uses client and server signals sent over a shared Wi-Fi network between the home computer and a Raspberry Pi on the rover. Our initial communication system uses 2 UEV point-to-point wireless bridges, each with 5.8 GHz of frequency, a 12 dBi directional antenna, 2 kilometers of transmission range, and power over Ethernet. Our system sends steering controls from the home base to the rover and sends video feed from the rover back to home base over the Wi-Fi. We are investing in upgrading our communication system to a more powerful one, which includes a Ubiquiti AirMax Bullet and AirMax Omni antenna with a frequency of 2.4 GHz, 13 dBi, and a 360-degree coverage for both the rover and home base. Our autonomous navigation system uses the Stereo Labs Z2i camera to stream live video feed from the rover and to assist with object detection. We use the OpenCV library to implement a Ruco marker detection. And similarly, we used OpenCV to implement a detection system for the color orange, which will help our rover identify specifically colored objects.
This year, for the programming, we decided to integrate everything within the ROS environment system. We decided to simulate our arm as well as a robotic base in ROS, and have programmed everything within Python and Arduino.
For our drivetrain, in terms of our programming, we have implemented a Raspberry Pi to Arduino system that sends signals from a controller to the actual base. The base first translates joystick input into Cartesian coordinates and sends these to functions designated for various driving configurations. These functions, stored in a Python script on our master Raspberry Pi, then send a unique number output to our Arduino through the Wi-Fi bridges. The Arduino then takes care of translating these outputs into specific motor speeds, which then execute the driving motion.
The science team has developed a 6-chamber carousel system for sample collection. It utilizes paper analytical devices, or PADs, developed at Notre Dame to detect primary, secondary, and tertiary amines.
The spinning carousel and stationary mounted camera, pump, and gas sensor let us run tests simultaneously and efficiently. Once the soil is deposited, the water will be pumped in and mixed with the soil. Then, a pad uses capillary action to facilitate 12 different series reactions and produce a color QR code unique to the substance that is being tested. We have tested this with an array of lifeless and life-rich soil to learn and recognize certain patterns.
We are so proud of the team this year and can't wait to keep moving forward. Thank you.